Okay, hi everyone. Today we're going to solve this problem that is, and it's a very popular problem as you can see. For sum problem. For sum is a very standard problem for arrays, maybe hash set, and binary search or two pointers. So these are the topics related to this problem. And mind it, if you have not checked yet, I'll be posting. I'm completing the Striver series, Striver SD sheet. So if you want to check, and there will be some upcoming, some other videos, upcoming videos that will be based on that particular sheet only. And if you want to check them out, you can. And this is like I think day 4, first problem. So from the Striver SDE sheet. So let's get started. So this is a medium problem, and 18th is the number. So the problem says that we are given an array of nums, array that is called nums of n integers. Okay, so the size of the array will be n. Return an array of all unique quadruplets. So we have to return an array of unique quadruplets. So let's see, what do we mean by quadruplet? Quadruplet means a group which has 4 elements in it. So 1 0 1 0, this is a quadruplet. 0 1 0, this is not a quadruplet because it has 3 elements into its group. And 1 0 1 0 0, and this is also because it has more than 4. So a group which has 4 elements into it, that is known as a quadruplet. And what do we mean by unique? Unique means, so in my array, so suppose in my array I have a quadruplet as 0 1 2 3, and another quadruplet is 0 2 1 3. So if you will look closely, the order does not matter. The order is not constraint over these quadruplets. So these quadruplets are not unique, because if we sort them out, then this is 0 1 2 3, and if we sort them out, then it is also 0 1 2 3. So they are not unique, and we should only have one occurrence of a quadruplet. We cannot change the array, change the order of the elements and say that this is a unique quadruplet. No, that's not the case. So this is the first thing, that we need quadruplets and we need unique quadruplets. Okay, now how to build quadruplets, let's see. So for these quadruplets, the elements will be inclusive of nums. So the quadruplet will be basically, this is a nums array, and these are some numbers. So we have to pick elements from this nums to form our respective quadruplets. And a b c d and a b c d should be distinct, which means that the numbers that we pick from nums array for our quadruplet should be unique, which means that, for example, we have nums as 0 1 2 and 3 4. So while making a quadruplet, so this is 0, this is 1, this is 2, and this is 3. Okay, this is 0, this is 1, this is 1, this is 3. This is not the case because 1 is only present once and at the first index. So we won't be storing an element or creating a duplicate element in a quadruplet. That is why 1 won't be there, and this is not a valid quadruplet. So another part of the question says that we will also be given a target value, right? This target value, and this target value has to be equal to the sum of the quadruplet. This might be a little confusing, but if we will dry run it on a test case, then it will be very simple. Let's see. So we will be given a target value, and this target value should be equal to the sum of the elements of that quadruplet. Let's see. So we have this test case, that is 1 0 minus 1 0 minus 2 and 2, and the target given to us is 0. Okay, now I want to see how many quadruplets do I have that will sum up to this target value, that is 0. So 1 minus 1 and minus 2 and 2. Yes, this is a valid answer because This quadruplet 1, minus 1, minus 2 and 2. So if we will sum them up, then 1 and 1 will be cancelled, 2 and minus 2 will be cancelled, so this will result in 0, and that is our target value. So this is a valid quadruplet. Then let's see if there are any other cases. Minus 2, 0 and 0. Yes, this is also right. This will also sum up to 0, which is our target value. Let's see some other quadruplets. 1, minus 1, 0, 0. If you can observe that the order is not mandatory, I'm putting them in a random order. So order is not an issue in this problem. And they will also sum up to 0, which is our target value. So these three are valid quadruplets. Let's see a quadruplet which is not valid. So for example, I take 0, I take 1, I take 2, and I take again 0. So 0, minus 1, 0 and 2. This will not result in 0, this will result in 1, which is not the target value. So this is not a valid quadruplet. That is how we have our three valid quadruplets, and we have to return an array which has these quadruplets. Just like this question, we are returning an array which has these quadruplets as its elements. Let's see another uh, let's see another example, another test case. So we have 2, 2, 2 and 2, and the target value is 8, right? Now the index are 0. Let's see. Yeah, the index are 0, 1, 2 and 3. Now in order to make a quadruplet, let's see, the first quadruplet for this will be 2, 2, 2 and 2, right? This is like a normal observation that these all terms will add up to 8, which is our target value. So this is a valid quadruplet, right? This is a valid quadruplet. Do we have any other choice? No, we don't, because if you take this one, this one, this one, and this is the order, then it will also result in this quadruplet. So despite or irrespective of the order, this quadruplet is the only answer to this example number 2, which is why we will be returning an array which has 2, 2, 2 as the only quadruplet, and that is our answer, right? So I think things will be much clear than before. And now we can focus on how to come up with a solution for this problem. Let's see. So the first approach for this problem is a brute force, as obvious. A brute force approach. Let's see how we can have this brute force approach. Okay, so for this brute force approach, what we will do is, so we have these numbers, that is 0. So we have these numbers, that is 0, 1, minus 1, 0, minus 2 and 2, right? Now let's see that how we can do this. So I will put a pointer I over here, j over here, k, and then l. Okay, and so basically this is like 4 nested loops, and this l will be traversing in this direction. Well, actually all of the elements will be traversing in this direction, and each one by one we are going to test for each element if the combination of I, j, k and l elements results into a target value, that is 0. Let's see. So now, yeah. So now I stationary, j stationary, k stationary, and L is the last nested loop. So nums of, or instead of, well, this is obvious as this is nums of I plus nums of j plus nums of k and plus nums of L, right? What is the value for this one? This is 1, 0, that is 1, that is minus 1, so it's 0 again, and this is 0. So this is target value. This is equal to 0, which means that we can say that if it is equal to the target value, and yeah, this is true. And if it is true, then we will simply just make a quadruplet that is 1, 0, minus 1 and 0, and put this quadruplet and sort this quadruplet. After sorting this quadruplet, I will push it in a set. So set is a data structure, and the set will be having its data type as int, vector int, and s, right? So set is a data structure in which you can insert and delete an element by the time complexity as log n. And if you have, for example, 0, 1, 1, 2, and if you want to put these elements into a set, they will be 0, 1, 2. Or if you have 0, minus 1, so these are the elements, then the set, so there are two things for the unordered set. So first thing will be that the elements will be sorted, and second thing will be duplicates will be removed, right? Duplicates will be removed, which means that minus 1, 0, 1 and 2, these are the elements that will be stored in a set. So I'm using the same logic for storing a quadruplet. That is why I have sorted them up. After sorting them up, this will be minus 1, 0, 0 and 1. And I'll be storing this, and I will be, just a second guys. Yeah. And I will be storing them up in a set. So this is a quad 1. And quad 1 is equal to an array of minus 1, 0, 0, 1. And this array is stored in a set minus 1, 0, 0, 1. And why I'm storing it in a set? So let's say, for example, now you get a new quadruplet, and that is minus 1, 0, 1, 0. Okay. Although it's very less probable that you will get this combination by the algorithm that we are doing. Yeah. But still, let's say that you get this quadruplet. And if we don't sort them up, then these elements and these elements are different. And we don't want this conflict, right? We don't want this conflict. So that is why after sorting them out, the new quadruplet will become minus 1, 0, 0, 1, which is now identified by the set that, oh, it's already present in my within my element, so I don't want this new element, and you can just not put this into my set. Well, we can insert it, but it will not be stored by the set because it already has that element. So we only have one copy of this quadruplet, and we won't be storing multiple copies. So that is the first algorithm. And then when we are done with this one, now let's increment our L to this pointer. And after incrementing it to this pointer, the value will be 1. The value will be 1, 0, minus 1 and minus 2. And now in this case, this is not equal to target value because this is minus 2 in total and the target value is 0. So this is not equal to it. Then we are not going to form a quadruplet or store it in a set. We are just going to simply continue with our iterations, and by continuing, I mean that we will be just incrementing our L. Now L is incremented and it's on the last element, and again we will have our 2 as the total of the summated value, and this is not equal to target, so we will continue with our L. And now the L is at the last, which means that the for loop containing the L iterations is completed, and now the control goes back to the k, and k will be incremented. So now k is pointing on this one, and we will see that this is 1, and the L is at the k plus 1 element, that is -2, and this is 1, this is 0, this is 0, and this is -2. Is this equal to L? Is this equal to target value? No, this is not. So we will now go back and increment our L. So now we have 1 0 0 2, and this is equal to 3, which is not equal our target value. So we will so the L iteration for loop is done, and now we will increment our k. Now this is 1 0 -2, and this is L. So yeah, this one, let's see, these are cancelled, and we have 1 as the final value. Now 1 is not equal to 0, so this one is also completed, and we have our k value on this side. Now the L value can, because L has to be equal to k plus 1, but k plus 1 is out of the boundary, so this will be reset, and j value will be incremented, and when j is incremented, k is equal to j plus 1, L is equal to k plus 1. So this is how new elements will be, and this for this certain iteration will keep on going. And if you want to see the code for this one, it will be very simple. That is, so first we have our for loop, and int I is equal to 0, right? Yeah. Then I has to be less than n. Let's say n is the size, and I plus plus, right? So the other for loop, nested for loop, will be for int j is equal to I plus 1, right? And then I is less than n, sorry, j is less than n, and j plus plus. Another for loop will be, another nested for loop will be int k is equal to j plus 1, and k is less than n as obvious, and k plus plus, right? And another for loop, this is the last one, int L is equal to k plus 1, and L has to be less than n, and L plus plus. Yeah. So in this way, we will be checking. So if our nums of I plus nums of j plus nums of k plus nums of L is equal to the target value, then we will be storing our quad, right? Then we will be storing our quadruplet. But if it is not, then we will simply just continue with your iterations and increment the L or K or whatever, right? And in storing our quad, this is the second operation. So in storing, we'll be using a set, and then we'll be storing them. So all this storing of quadruplet in a set is kind of like a very tedious task, right? So this problem can be sorted out if we are sorting them up. So this was, excuse me, yeah. So this was the example, and if we sort them up, so if we sort them up, this is going to be, so after sorting them up, yeah, this is going to be -2, yeah, -1 0 0 and 1 2, right? This is I, this is j, this is k, this is L. Well, the problem will be same if we don't have a way of eliminating the duplicates, and for that we will have a simple while loop that for example, we are on this element and we have studied, let's say that we have our elements as, just a second guys, yeah, 0 I j k, 0 again L, Now 1, 1, 1, 2. Yeah. So these are our elements. These are the elements that we have, the sorted elements. And now I want them to be, let's say I am on, so let's say we are studying this, let's say we are studying, yeah. So this is K and this is L, right? So the sum will be, what will be the sum? It will be minus 2. Now we know that minus 2 is not equal to our target value, right? Minus 2 is not equal to the target value. So we don't want this combination where I is this J and KL, right? We don't want this combination. Then we iterate our L to the next element. But wait, the previous combination was 0 and 1. And the next combination is minus 1, 0 and 1. Well, they are same. Okay, if they are same, let's increment it to the other one. They are also same. Okay, let's increment to the other one. Yeah, now they are different and now we can study them. So in order to deal with this mess, what we can do is we can have a while loop in which we can say that if I plus 1th element is equal to the ith element, till then just simply keep on incrementing the pointer. So we will, so for this particular example, this will be L plus 1 and this will be L and this will be L. So we will be incrementing L until and unless we found an element that is not similar to the previous L value, right? This is the new concept, and this is a very good optimization because we won't be studying, we won't be storing the similar elements, and by this concept we won't even need what do we say, a set or a data structure to eliminate the duplicates. So this is like a good optimization. Now I think we had our enough. We should go to our next approach. And first, so just to complete this one, this approach will take order of, as you have guessed, there are 4 nested loops. So it will take n to the power of 4 time, and space complexity. That will be, so if we are using, let's say, so space complexity will be 1 if we are using set. But if we are not using a set and we are sorting the elements, then the space complexity will be n if we are using a set, and if we are not using a set, then the space complexity will be constant because we are not using any auxiliary space. Although we will be using a, let's say, like a returning array of the quadruplets, but that is something that we are returning. So ignoring that, because that is a mandatory part and we need to return it. Ignoring that, we will have our constant time complexity, and but this one we will have n complexity. So these are the complexities for the first approach, that is brute force. Now let's see the second approach. So the second approach is little efficient, in which we will have 3 pointers, and for the last element, because obviously we need 3 elements of the quadruplet, and now we want to find the last element, and in order to find the last element, we will be using binary search. Binary search, right? Okay, so now let's see how we can use this. So we have our example, and because it's a binary search, so I think it will be automatically in your mind that the array has to be sorted now. Because earlier we were sorting the array to avoid using a set data structure for the storing of duplicate elements, but this time we are using binary search. So it's not optional for us to sort the array or not sort the array. We have to, sort the array. So after sorting the array, the elements will be -2, -1, 0, 0, and 1 and 2, right? These are the elements. So let's place our pointers. This is I, this is J, this is K. And now we want to search the last element. So let's see the sum till now. So till now the sum will be -3 and the target value is 0. So we have to add something with 3 so that we have 0, and that will be 3, right? We have to add something with -3 to add to have our final result as 0, that is a target value. So we need 3. And let's perform a binary search on this subarray to find 3 if we have 3 or not. And to perform binary search, it's pretty simple. We have our low pointer, and then we have our high pointer, then we have our middle computed by them, obviously computed by the low and high pointer. So we have 3, and then we will apply binary search on these, on this little subarray, and we'll find and we'll look for an element. So unfortunately 3 is not present here, so we will simply increment. So we will simply increment k, and now their sum is equal to, again it's -3, and so we can obviously optimize this one as well. So if k value is similar to the previous value, then we don't need to place the value or study that point, because we have already studied that point. So we will increment k to this side, right? I think things will be now pretty much clear. And this value, this sum will be -2 plus x is equal to the target, that is 0. So x value will be 2. Now we need an element that is equal to 2 into this subarray, the remaining elements. And fortunately we have our L pointer, or not the L pointer, the middle element, because this is low, this is high, and this will be the middle according to the binary search. So we have our element, and then we will store this quadruplet, that is -2, -1, 1 and 2. And we don't need to worry about the duplicates because this is a sorted array, and we are obviously, for example, this case, when we find that the kth previous value is same as the current values, we just increment the k until the value where the k new value is different to the previous value, right? So that is why we don't have to worry about the duplicate. So this is our first quadruplet, and similarly we will have our multiple quadruplets. So this is a third approach, and if you can see, then these are the naive implementation of 3 nested loops, which means n multiply by n multiply by n multiply by. So at the remaining part we are applying the binary search, and the maximum elements in the remaining part would be n minus 3. So that's pretty much similar to log of n, right? So because of this, the time complexity will be n cube log n, n cube log n. And space complexity, we are not using any auxiliary space, although we are using a space to store our quadruplets, but that is not counted, and because that is like a mandatory step for the problem, and according to the implementation provided to us by LeetCode. So I'm not counting that as an auxiliary space, so that is why the auxiliary space will be constant. Now let's see if we can improve, because this is like a pretty good approach, and let's see if we can improve from this approach as well. So the third approach, right, the third approach, yeah, the third approach is 2 pointers plus 2 pointers. Let's see this approach. So if we recall our elements, they were -2, 1, 0, 0, 1 and 2, right? Now I will place these 2 pointers. So I will place these 2 pointers, that is I and j, okay? And now I will place another 2 pointers, let's say low and high here. Now what I will do is the nums value, so I will calculate the sum till now, so that is -1, and the sum that I will have from these pointers. So I think now you will get the point that this is a sorted array, this is a sorted array, and the required number is 1. We need to find 1. We need to find the sum which is equal to the 1. And because it's a sorted array, we can use two-pointer traversal technique to find a particular pair of elements which will result in the required number. That is 1, right? So 1 is a required number. Let's see. Now 1 is a smaller element as compared to the low, because now the sum, let's say the low and high, I'm sorry. Yeah. So this is our low and high pointers. So at first the low is 0 and this is 2. Now this is equal to 2 and 2 is greater than the required number, that is 1. Because it's greater than the required number, we will be moving our high pointer, because if we decrement our high pointer, then the overall sum is destined to decrease, right? So now we will have our low as 0 and high as 1, and this is equal to 1 and this is equal to 1, which means that now we have our quadruplet. So our quadruplet will be -2, 1, 0 and 1, right? 0 and 1, this is our first quadruplet. Okay, let's see if we can have more. Yeah, let's see if we can have more quadruplets. So now I will increment, now I will see that can I have something else. Obviously if I will increment our L pointer, right now our L, so this is our low, this was our high, and now if I increment our low pointer, right, then it's not going to be beneficial for me. Why? Because we are going to end up with the same one. So that is why the same optimization we are going to use, that if the low of previous pointer is equal to the current element, is if the element pointed by the low pointer, previously pointed by the low pointer, is equal to the current element, then we will simply just passed on to that element. So I was here initially and now I am here, but the issue is that this is similar to the element which I was pointing on earlier, the low pointer. Now low pointer is at this place, and it's pretty obvious that we are given in the question that A, B, C, the index of these quadruplets have to be unique. We cannot store a single element from the nums array twice in a quadruplet. That is why we will be terminating our while loop for the two pointers when low is equal to high or low has crossed high, and then we will increment our the parent nested loop, that is jth element, right? Now j will be incremented, so j is now pointing on this one, and this sum is equal to -2. Now the required number that we are looking for is 2. So because 2 plus -2 is equal to 0, that is our target value. And this is our low pointer, this is our high pointer. Let's see if we have the sum that we want. Yeah. So low is equal to 0, high is equal to 2, this is equal to 2, and this is equal to the required num, right? The required num, that is 2. So this is our another quadruplet, that is -2, 0, 0 and 2. This is our another quadruplet. So similarly, we will be storing the quadruplets in such a way that we don't have duplicates, because we are taking this into account that the new element pointed by a low pointer or a high pointer or even a j or ith pointer is different than the element that is pointed by them earlier, right? So this thing will take care of duplicates, and this is also a good optimization technique. Now the final code for the whole implementation is, just a second guys. Yeah, so this is the final code, and in this final code we have, so first of all we have our answer in which we are going to store all the quadruplet. That is why it's a 2D vector, and then we are going to sort. So this is the first thing that I've told you, we should be sorting the array. And then this is our ith pointer, right? This is our jth pointer, right? And then we are going to calculate the required num. The required num, and there could be overflows, that is why I am typecasting them into a long data type. And the target minus nums of I, nums of j, this will give us the required num. And then we are going to apply a two pointer search on the remaining segment of the array, and that segment is sorted because we have already sorted the array in the initial step, that is here. Now we have a low pointer that is equal to the j plus 1, as obvious, because we tend to have unique elements. We cannot overcount, we cannot simply store a single copy or two copy of an two elements from an array, despite of the fact that there is only one existence of that element. Then we have a high pointer, that is nums dot size minus 1. Then we have a low should be less than high. This is pretty standard, because if they are equal to high, then low and high will be pointing on the same element, and even if it satisfy our answer, then it should not be the case, right? Because we want to store unique indexed elements. Then we are going to have a check. So check is a number which will have a low and high value. Now if check is equal to required num, then we will take that as our quadruplet and push that quadruplet into our answer array. And then this is an optimization which I have told you, that if we have our current element is equal to the previous element, then we don't need to study or process that element, we can skip that element. So to skip that element, I'll be increasing the pointer, and similarly the high pointer, because high pointer, it has to be decremented, so it will be minus minus decremented. Now if check is less than num, required num, that means that we need to increase our check variable, and check variable is num of low plus nums of high. And if we want to increase the nums of low and nums of high, we have to basically increment the low pointer, because if the low pointer is incremented, the upcoming element will be greater. And if the check is greater than the required num, now we need to decrease the check, and in order to decrease the check, we need to decrement the high pointer. And similarly for the logic that I have explained you here, that we want to skip the already processed elements, or the similar elements, will be incrementing j with this rule, that j plus 1, if nums of j and nums of j plus 1 are equal, then we'll be just incrementing it, and we'll be incrementing I, and at last we'll be returning our answer, which will have all the required nums. And I think this is the time complexity. Yeah, the time complexity for this solution will be n cube, right? This will be n cube, and space complexity will be constant. So these are the two. I think this is the most optimized way. If there are any other optimized way, you can let me know. And if you want to know the source code, if you want to take a look at the source code, then I will provide a GitHub link in the description, and you can check the source code. So this was the problem, and thanks for watching.